when we try to apply a mathematical result, we want to make sure that we check the conditions properly. And if we forgot to check the conditions, it may lead to very unexpected results. The Bernoulli rule has many conditions, so you want to make sure that you check all the conditions before you really apply the result. So let's look at a problem and see what we mean by this. So how about this problem? So let's say we have find the limit when x goes to 1, x squared minus x minus 2 divided by x squared plus 2x minus 3. So let's say we did not check the conditions much, and then we take the derivative and plug in the result. So let's say is a limit. So x goes to 1. So the derivative at the top is 2x minus 1 and divided by 2x plus 2. So and then what we do, we're going to plug in the plug in x equal 1 here. So when you plug x equal 1, what you get is 1 over 4. But unfortunately, this answer is completely wrong. So that's not what you get. So this limit actually does not exist. But instead, what we get is 1/4. So you need to be very careful with when you work with results like that with many conditions. You really want to make sure that you actually check all those conditions before you really apply. So let's try to recall what the Bernoulli rule is. So Bernoulli rule applies when you have a fraction when x goes to infinity. When x goes to a, you get either 0, 0 or infinity of infinity. So there are two cases. So if this is the case, so that means the top and bottom goes to either 0, 0 or infinity to infinity. So in this case, what will happen? But the rule says that when x goes to a, so the same limit you can obtain by taking the derivatives first and then take the limit. First you take the derivative and then take the limit if, this is the most important, if the limit on the right hand side exists. And then also we have one more condition. So here we know that the x prime a, so when x goes to a, so you want to make sure that this doesn't equal to 0. So this is not equal to 0. So sometimes that can happen. So those are the special conditions that you want to worry about. So that doesn't equal to 0, and also the limit on the right hand side exists. So that's exactly what happened in the previous problem. So now let's try to see the problem back and see what went wrong. So now let's see what exactly happened when x goes to 1 in the problem. So for that, what we're going to do is we're going to look at the factors of the denominator, and you can see that the factors of the denominator are x minus 1 and x plus 3, and you have x squared minus x minus 2 in the numerator. And then when x goes to 1, and you can see that the numerator actually goes to -2. The numerator gonna go to -2. But what will happen in the denominator? Denominator, because of this special factor, you can see the denominator goes to 0. So what you get is a fraction like -2 over 0, which doesn't have a meaning in mathematics. So if it is a x goes to 1 plus problem or 1 minus problem, you can actually get an answer for this one of those infinities. But when it goes to 0, we really don't know what exactly happened, because you get two different answers. Because if you go from the positive side, it goes to positive infinity. If you go to the negative side, go for the negative infinity. So we don't know which infinity. So that means in this case, what will exactly happen is this limit does not exist. The reason is numerator goes to -2, the denominator goes to 0, but we don't know which side. Since we don't know which side, this really doesn't have a meaning, so that means this limit does not exist. So that's the correct answer for this one. But if you just use it without checking the conditions, and you will see that you get a wrong answer, 1/4. So what is the problem here? So what we did wrong? So one thing that we did wrong is we did not check whether this is a 0 over 0 problem. So you can see when x goes to 1, the numerator is -2, but the bottom is 0. So it is not a 0 over 0 problem. It's like a -2 over 0 problem. So if this is the case, you actually cannot apply the Bernoulli rule for this problem, because it's not a valid condition. That's not a valid condition here. So that's one thing. And also, even if it is 0 over 0, you want to check whether the limit on the right hand side exists. So there are two problems here. So one problem is doesn't apply because it's not a 0 0 or infinity problem, and also the limit on the right hand side does not exist in this problem. So that means there are two problems for this one. So so you want to make sure that when you try to do a problem like that, you check the condition properly. So let's look at another problem. So again, so this answer is wrong. So this is the wrong answer. The answer is wrong. That's not the correct one. Correct answer is does not exist. Okay, so let's go to the next problem. Let's look at this problem now. We have limit when x goes to infinity, x minus sine x over x. This problem may look very familiar to you. Normally, like we have x goes to 0, and then you can see the numerator goes to 0, the denominator goes to 0, so we use the Bernoulli rule. But in this case, we have x goes to infinity. So x goes to infinity, x minus sine x over x. And you can see that even in this case, when x goes to infinity, since you are just subtracting sine is always between 1 and -1. So when you subtract from x going to infinity, so you can see that it is infinity over infinity problem. So let's say without worrying about the conditions, you just use the Bernoulli. So we take the derivative. So when you take the derivative, you get 1 minus cosine x divided by 1. So, but you know that the cosine is oscillating. So the graph of cosine is like that. So that means the cosine function is fluctuate between 1 and -1. So that means this limit when x goes to infinity, you can see that if it is 1, you get 0. If it is -1, you get 2. That means you get values between 1 and 2. So that means this limit does not exist. So you will say, okay, limit does not exist. But the problem is that's not the correct answer. This answer is wrong. The reason is, remember when you look at the Bernoulli rule, so we check the condition. The first condition is infinity or infinity problem. So everything is okay. And then another condition is the denominator function should be differentiable at the point, and it's 1, so it's differentiable. So what's the problem here? So there's something wrong. The problem is in the Bernoulli rule it says that they are equal if the limit on the right hand side exists. But problem here is the limit on the right hand side does not exist for this problem. So that's the issue. So that means this argument is incorrect. So argument is wrong. So argument is incorrect because we did not check the last condition. Last condition says the limit should exist. So let's see what's the actual answer. So let's say, so it's a limit when x goes to infinity, x minus sine x over x. So what we can do is we can actually divide this one. So you can say if you divide by x the two terms, so you're going to get 1 from the first one. The second one you get sine x over x. That's what happened for the second term. And then since we know that sine x is always in between 1 and -1, sine x always in between 1 and -1. So when the numerator goes to infinity, it is something a fixed number. You can say like 1 is the maximum value. So it's 1 over large number. That means this whole fraction goes to 0. So this fraction goes to 0. So that means your final answer simply become 1. So the 1 is the correct answer in this case. But instead, if you use the Bernoulli rule in an incorrect way, you get it does not exist. So you have to be very careful with this one. You want to make sure you check the conditions properly. So let's look at another problem. So you can see that this is how important it is. So let's look at another problem. Suppose we have this problem, limit x goes to 0 plus ln x over x. Let's say we do not check the condition and just take the derivative and try to apply the Bernoulli. See what happens. So limit when x goes to 0 plus, so we take the derivative of the top, so which is 1 over x, and the derivative of the bottom is 1, and you can see that, so it's a limit when x goes to 0 plus 1 over x. Now when x goes to infinity, when x goes to 0 plus, you can see 1 over x goes to positive infinity. So you get the positive infinity as the answer. But this answer is actually incorrect. So you will see that in this problem, this is the right argument. So we have limit x goes to 0 plus ln x of x. Remember the graph of ln x? So you know the graph of ln x looks like that. So that means when x goes to 0, you can see function goes to negative infinity. So that means what happens is the numerator goes to negative infinity and the bottom goes to 0 plus. So that means you try to divide by a very small number. When you divide by a very small number, your answer gets larger. So that means what you're going to get is you're going to get negative infinity. So you're going to get much and much more larger values. So because the negative sign is called negative, so negative infinity. So the actual answer is negative infinity. But instead, if you apply the result row in an incorrect way, you end up getting positive infinity. So be careful with these kind of problems. So you want to make sure that you check the condition. So what happened here is you can see the top goes to infinity, the bottom goes to 0. So this is not a correct type of problem. So you can just take the derivative. But you can actually do this problem in a different way. So if you move one term to the other side, or then it's going to be infinity times infinity or 0 times 0. So so those are like you can handle in a different way, but again they are not a Bernoulli type problem. So this is not a Bernoulli type problem. So that's the problem here. Okay, so let's look at another one. You remember this problem when x goes to 0, this is like very familiar problem, sin x of x. So let's say again without checking the condition, you just take the derivative. So limit x goes to infinity, sin x means cosine x and the bottom is 1. So now what happened is we know that the cosine is a fluctuating function, it's an oscillating function. So it's going to oscillate between 1 and negative 1. So it's a 1 and negative 1. So that means when you try to find the limit, you can see that it looks like it's going to go between the two different values. So you might say wrongly or limit does not exist. So that might you might say limit doesn't exist in this one. But I should say this answer is wrong actually. So let's see how we can actually get the answer properly. So you can see this is not like a difficult problem. So you can see x goes to infinity. This is sin x over x. And you can see that we know that the sin x is always in between 1 and negative 1. So sin x always in between 1 and negative 1. So because of that, since the 1 and negative 1, so the top is bounded. It's bounded by 1. So what will happen is numerator getting larger and larger and larger. So this gets larger and larger, but top is bounded. So that means your answer is simply going to be 0. So the 0 is the correct answer because the top is bounded. It doesn't get large, it's bounded, but the bottom is getting larger and larger. So it's getting like a smaller and smaller and smaller fraction. So you end up getting 0 as the answer. So 0 is the correct answer. But instead, if you use the Bernoulli in a wrong way without worrying about the conditions, you get doesn't exist as the answer, but which is incorrect. Let's look at this one. This is a very interesting problem. So we have limit when x goes to 0 plus ln x minus 1 of x. If you just do not check the condition, it may look like infinity minus infinity, but actually that's not the case. So let's look at the graph. If you look at the graph, you can see the log behave like that. So that means when x goes to 0, you can see it goes to negative infinity. So it's not infinity minus infinity, it's a negative infinity minus negative infinity. So if both are negative infinities, and you can see that there is no ambiguity here. So you know that they both decreases indefinitely. So that means the final answer is negative infinity. That's the correct answer. So that means here you don't have to do any more math here, because you just look at the graph and you can see the behavior of the function, and you can see that when x goes to 0 plus ln x decreases. So that means you're going to get negative infinity as the answer for this one. And also if you are not familiar with the graph of 1 of x, and you can remember this is like what we call rectangular hyperbolas. So you get a graph like that. That means go to 0, like go to negative positive infinity. With the negative sign you get negative infinity. So that's what happened. So the answer is actually negative infinity without much math, just like a simple argument. So let's look at another one. So we have limit x goes to infinity x to the x, and we did a similar problem x to the x, but when x goes to 0 plus. But now we have x to the x, and you can see clearly here. So this is it's an infinity to an infinity problem. This is not an indeterminate form. If you infinity to an infinity, it's getting larger and larger. So that means the answer is simply infinity. So you don't have to do any log or anything like that for a problem like that. Okay, so let's look at another one. So we have x goes to 0 plus x to the 1 over x. So what will happen when x becomes smaller and smaller but with a positive number? So you can see x goes to 0. When x goes to 0, 1 of x goes to infinity because it gets larger and larger. So it's a 0 to infinity problem. When you have 0 to infinity problem, again there's no ambiguity here. So 0, you get more and more larger and larger power, so you get the fraction gets smaller and smaller and smaller. So that means you simply end up getting 0 here. So there's no ambiguity here. The answer is simply 0. So don't try to use Bernoulli for these kind of problems because it doesn't apply, because it's like a different type of problem. Okay, because it's actually easier, much easier compared to other problems. And the same thing will happen for this problem as well. So let's say limit when x goes to 0 plus, not 0 plus, let's say infinity. Let's switch them. Infinity, let's say 1 of x to the x. So this problem is very similar to the previous one. So when x goes to infinity, you can see the first one goes to 0, 1 of x goes to 0, and x goes to infinity. So 0 to the infinite power. So in this case, again, what will happen? It's the same type of problem. So what will happen? 0, and you're going to increase to larger power. So what will happen? Get smaller and smaller and smaller. So you end up getting 0. So the answer is 0 for this problem as well. What about this problem? So we have when x goes to infinity, sine x plus 1 over cosine x plus 2. And you know the graph of these two functions. So one go like that, that's a sine one, and the other one go like this, so it's a cosine, so go like that. So, and you see that they fluctuate between the two values, so there's no any special trend that they are going just fluctuate between the two. So that means in this one you cannot apply any Bernoulli rule here, because none of them goes to infinity. They just fluctuate between two different values. So it don't go to 0 over 0. So it's not 0 over 0, or it's not infinity over infinity. None of them. So that means what will happen in this case is the limit does not exist, because it's not a one value. It just fluctuate between values. Okay, actually fluctuate between negative infinity and positive infinity, because because the bottom can be 0 or finite value. So it can be between positive infinity and negative infinity, because the bottom switches the sign, and the top also switches the sign. So it's going to go between positive infinity and negative infinity. So that's what happened. Okay, so let's look at one more. Let's say you have limit when x goes to infinity, x to the power 1 plus e to the negative x. We know graph of e to the negative x. Graph of e to the negative x means like it's going to go and decreases and go to 0, pass through 1. So that's a graph of e to the negative x. So that means when x goes to infinity, this term goes to 0. So that means this problem look like infinity to 1 type of problem. Infinity to 1. So when you have infinity to 1, this is very clear, because you can see that there's no ambiguity for this problem. So that means this gets larger and larger, so the answer is infinity. So you can see that. So when you get a problem, so always think about like what's going to happen first, whether this is a indeterminate form or like a standard one. So the indeterminate forms, you're going to get 0 over 0 and 1 to infinity and infinity to 0. Those are the indeterminate forms. But if you have like 0 to infinity, that's not indeterminate. And if we have infinity to 1, that's not indeterminate. Those are very clear. And then also 0 to 1, like things like that. So if you get things like that, these are not indeterminate. We know exactly what the value is. And also sometimes what happen is earlier we got like infinity plus infinity, or negative infinity, things like that. So those are not indeterminate. Those are exactly very clear what the answer is. Okay, so that's about this. So I hope you learned something in this one, and then this can help you for your studies. So thank you for watching.